Okay. Thank you, Eric, for your very kind introduction. So today I'm very happy to share the latest work, Quasi-Monte Carlo with a random Hankel digital net. This is a joint work with Takashi Goda and Professor Raoul. So the topic will be the digital net for Quasi-Monte Carlo. And here, first, I want to give a brief introduction for the digital net and Quasi-Monte Carlo as well. So we use Quasi-Monte Carlo to approximate the integral given in this unit hypercube. And then in Monte Carlo, we know that we use ID random samples to give a Monte Carlo estimator. And then in Quasi-Monte Carlo, we use the deterministic point sets. Here we denote it as xn, and these are deterministic, and then these points can be designed such that they have a good uniformity in this unit cube. Among the many quadratures in the Quasi-Monte Carlo, today we'll talk about the digital nets. It allows the algebraic construction over this finite field FB. It's possible to scale to high dimensions, and it's also compatible with various methods of randomizations. So some examples of digital net include the Sobel sequence, polynomial lattice root, and etc. So we will talk about this digital net that is parameterized by this three parameters, TMS net. So this is a set of b to the m quadratures in this unit cube. B is usually chosen as a prime number. For example, it can be 2, 3, 5, or other prime numbers. And then as we increase this m, then we expanding the quadrature points. And then we can divide the unit cube into these elementary intervals such that each of these elementary interval will contain exactly the same number of points, so that if we can let this t to be smaller, decrease this t, then we have each of these smaller elementary interval will contain exactly the same number of points. So this implies the higher uniformity. So that's why the smallest t, such that this property that satisfies is also called the quality parameter. And this t is determined by the generating matrices. So roughly speaking, the higher the rank of these generating matrices, the smaller the parameter t. So we want these lines of these rows of these generating matrices to be linearly independent as much as possible. And then finally, S is this integration dimension. So we have already mentioned the generating matrices. We need these matrices to generate a digital net. We choose B to be a prime number, and we want to generate B to the power m points. We have this S. So totally, in each dimension, we have a generating matrix, and then in total, we have S generating matrices. And then for n, okay, so I haven't mentioned about this. So m is so basically b to the m is the number of points that you want to generate. So we can order these points by n. So n is ranging from 0 to b to the m minus 1. And this capital E is the precision. So in many, including this paper, that we are going to assume that we have infinite precision. So in the analysis, we are going to assume that this capital E is infinite. But in practice, we are using this floating point arithmetic in the computer simulations. So this E is typically finite. So for example, if we're using the double precision and then choose B equals to 2, then this E, usually we choose this capital E to be 53. So corresponding to this double precision floating point arithmetic. So this n is an integer ranging from 0 to b to the m minus 1. We write this n in this b-add expansion, and then we use this n with arrow to be this vector containing this digits in this b-add expansion. And then we multiply the generating matrix with this vector n, and we get another vector also consisting of these integers from 0 to from 0 to b minus 1. Then we have the digits of b-add expansion of this y, and now we're using these integers to construct this quadrature point. So this is x and j, the nth point in the jth dimension. J is from 1 to s, and then it can be 1 to b to the m, but okay, so here I think this should be from 0 to b to the power m minus 1. Okay. And then we get this quadrature point in this digital net. So this is about the construction. So we see that the construction will highly depend on the choice of this generating matrices. For example, in the Sobel sequence, the generating matrices will look like this. Sobel sequence is a base 2 digital net. These matrices are upper triangular. On the diagonals, these entries equals to 1, and in this other part, this is either 0 or 1. And there's a freedom to optimize these strictly upper triangular entries. So this work optimizes these generating matrices in terms of the two-dimensional subprojections. And the result is widely implemented in various softwares. So these generating matrices, CJs, are deterministic. But recently, there has been interest in the randomized construction of these generating matrices, because in the case of a deterministic construction, it may require data as input. For example, the optimized this generating matrices, we need these tables as input. And even though the dimension can be already very high for most of the applications, there is maybe a limit on the maximum dimension because we have only limited data. So now there are some work studying the randomized construction of this digital net. And so essentially, we don't need any data as input. And we can, this method can be scalable in dimensions. It can be go arbitrarily high as long as we have enough running memory. And one of the feature is that the choice of the base B can also be flexible. So we don't have to only consider the base 2. This choice can be general. So here I want to mention two methods on this randomized generating matrices. The first one is proposed by these two work. These authors propose this randomized polynomial lattice rule. So I will not go into the details of polynomial lattice rules, but the approach is to randomly sample polynomials, numerator polynomials and denominator polynomials from specific admissible sets. So what I want to emphasize is that in polynomial lattice rules, the generating matrices have a Hankel structure. So basically, Hankel structure is that the next row of the matrix will basically be the same as the previous row, but shifted by one place. And then the other work by Pan and Owen, they consider to generate the construction matrix, generating matrix and each term is sampled uniformly from the FB. So, for example, if we consider base 2, then each of these terms is sampled uniformly from either 0 or 1. And we refer this method as the uniform random design. So our work is, we can consider it's motivated by this two work that we combine the feature from both of these two methods. We propose the Hankel random design. We'll also consider the randomized construction of the generating matrix. And the generating matrix, we have this Hankel structure. And now instead of choosing each entry uniformly, we will only choose a vector such that this vector is of length e plus m minus 1. And each entry in this vector is id from fb. And then we construct this Hankel matrix. This is for 1D, and then for multiple dimensions, we just generate these generated matrices independently across dimensions. Okay, so now we talk about the error analysis. For digital nets, we can use this Walsh analysis and the duality theory to express the integration error in terms of the summation of this Walsh coefficients in this dual net. So the error is driven by this Walsh frequencies in this dual net. And since that we now have the randomized construction of the digital net, we need to study the probability given an index k that belongs to this dual net. So what the result we have is that our result is that for Hankel random design, the probability for any fixed k that is non-zero, the probability of k being in this dual net is given by b to the power minus m. And this is the same as the one in the uniform random design. With the random digital shift, we get unbiased estimator for both Hankel random design and the uniform random design. But we also notice that the mean squared error is only n to the minus 1 times the variance of the integrand. So this is the same as the case of Monte Carlo. So we don't have any advantage from here. So this motivates us to use appropriate estimator, for example, the recently studied the median of means QMC rule. So why we are using the median of means is that we know that in this scrambled digital nets, there are certain events, we call it the bad event, such that they dominate the error. As we mentioned earlier, that the error is driven by these Walsh coefficients that belongs to this dual net. So there are some frequencies that may have a larger component, larger contribution to this error. So we identify these indices by this set capital K, and we define this bad event by this event. So when there exists K belongs to this set capital K, such that this index K belongs to this dual net. So one can think about the complement of this bad event is that there doesn't exist any K from this set capital K that contributes to the error decomposition of the digital net. So in that case, the error can be made smaller. And now we want to study what is the probability of this bad event. Intuitively, we can use the union bound to bound this probability that this bad event happens, which is the cardinality of the set times the probability of each k that belongs to this dual net, which is b to the minus m. But this bound will give us the same result for both the Hankel random design and uniform random design. And what really distinguishes these two methods is to consider the joint inclusion probability. So that is given both K1 and K2 that belongs to this set capital K, such that they belong to this dual net at the same time. So what is this probability? And how do we use this probability is to use this two probability bound. The Chung-Erdős bound gives us the lower bound of this this union probability, and then we have this Hunter's bound to give us the upper bound for this union probability. So we want this joint inclusion probability to be as much to be higher, so that we will have both. We will have the lower bound for both the a lower probability for both the lower bound and this upper bound. Okay, so okay, this is kind of heavy, but for both type of randomized design, this joint inclusion probability is equivalent to this event, where this generating matrix C transpose times K here K is the matrix that consists of these two vectors K1 and K2, that the result equals this zero matrix. And we can derive that the result, we call it Y, so C transpose times K, is uniformly distributed on the linear subspace of this image. So we call this Vj as the dimension of this linear subspace. For the uniform random design, the dimension of this Vj is either m or 2m. But for the Hankel random design, the dimension of this Vj will when the rank of this k is 1, then the result is the same as the uniform random design. But when the rank of this kj equals to 2, then the dimension of this Vj can be it can be between m plus 1 and 2m. So this is a lower dimension compared with this 2m, and that will result in a higher probability of this joint inclusion. And in the next page, we're going to give a intuition of this. So for simplicity, we consider base 2, and we let K1 just equals to 1, and then K2 equals to 2. So in this binary representation, this K1 will, this 1 will represent, corresponds to a vector of this first one. So we only have this 1 here. And K2 corresponds to this vector. So the result of this multiplication will be the first two columns of this C transpose. So one can see that the dimension of these first two columns is just okay, I think this should be 2m. So the dimension will be 2m. But with the Hankel random design, this result will also correspond to this first two columns, but the dimension will only be m plus 1. And eventually we can prove that, for example, when in one dimension, when b equals to 2, the probability of this Hankel random design, the bad event in this Hankel random design, is less or equal than the probability of the bad event in the uniform random design, which is in this case we can also lower bound this probability. So this would be theta of the cardinality of k times 2 to the minus m. In the end, we'll have some numerical results to show the advantage of the Hankel random design over the uniform random design. So since we studied the probability of this randomized design, the probability of a given k that belongs to this dual net, and we also want to revisit this linear matrix scrambling. What is the probability of a given k that belongs to this dual net? So with this linear matrix scrambling, one usually choose this CJ as deterministic matrices, generated matrices, for example, the Sobel sequence. And then this matrix M is the randomization, so it has some structures. And we derive the probability bound for a given k that belongs to this dual net. So if this k, the frequency is small, then the probability is 0. So that doesn't contribute to this error expansion. And when this k is very large, then the probability is the same as in this both the Hankel random design and the uniform random design. And in the intermediate regime, we have this probability bounds that can be substantially larger than b to the minus m. So in this regime, the probability for this HRD or URD is much smaller than this probability in this linear matrix scramble. And with this result, we can also connect these two randomizations in this digital net, the oven scrambling or the linear matrix scrambling. We derive this probability, and we find that we use this identity to connect these two properties. So this left-hand side is the probability term that arising from the linear matrix scrambling. And this right-hand side is the gain coefficient that arises from oven scrambling. So we use this identity to connect these two properties. And the consequence is that we can show that the variance is the same for the digital net under the oven scrambling and the linear matrix scrambling. And then we'll discuss the error analysis and the proper choice of the function class. So we propose this weighted Sobolev variation space. This is the function class that the function that we want to study. This is almost look like the weighted Sobolev space, except that in the middle we have this Vitali variation. So without this part, then this would be similar to the weighted Sobolev space. The reason that we propose this function space is that we study the summation of the Walsh coefficients from a certain class, and we find that this definition is a natural upper bound for these Walsh coefficients. And then we present the result. Okay, so in this work we have studied two types of estimator. The first one is the median of means estimator. So we have let's say a few 2R minus 1 RQMC replica, and then we take the median of this result. And the mean squared error of this median estimator is bounded by this two term. So roughly speaking, the first term corresponds to this good event. So that is more than half of the estimator are in this regime, then the median must be in this regime. So this part enjoys this fast convergence rate. When we take epsilon to be close to 0, theta to be close to 1, we have a convergence rate that is alpha plus p plus 1/2. So alpha is the differentiability of the function, and then this p is the order in this Vitali variation. So the second part is about when the more than half of the estimator fails, then the median estimator will be in this regime. But the integration error is still bounded by this L infinity norm of the integrand, and then we can increase R, that is the replica of this RQMC, to reduce this second part exponentially. And we also discuss in which case the convergence rate can be dimension independent. If we're using this product weight assumption with this summability of these weights in the definition of this weighted Sobolev variation space, then this constant can be bounded independently of S. And notice that this alpha plus p plus 1/2 is exactly the convergence order in here. So the second estimator is what we call the greedy optimization estimator. As we mentioned that we will construct this generating matrices randomly. So the first step we can do is that we generate so our replica of these generating matrices, and we choose the one that minimizes a certain worst case error bound, and then we will just perform the usual randomized RQMC on the chosen design of this matrix. So here we have this high probability worst case error bound that the error is bounded by essentially b to the minus m to the power 1 over lambda. And when lambda is close to 1 over alpha plus p, we get the convergence rate alpha minus alpha plus p. And here the corresponding dimension independence dimension independence condition is that the summability of these gammas to the power 1 minus alpha plus p that corresponds to this worst case convergence rate. Okay, so we have introduced these two estimators. Now we'll give a comparison. The median of means is it can be universal because we doesn't need to know the prior smoothness information, and the estimator is biased. From this greedy optimization, we need to know the smoothness of the integrand because we need to know the computable worst case error bound. But this method can be very efficient when the function evaluation is expensive. For example, when sampling involving solving a differential equation, then the optimization procedure will be relatively cheaper than this sampling procedure. And the estimator is unbiased, so that for example, when one is interested in the unbiased estimator, this can be an option. Okay, so now we go to the numerical results. We will study this test function given by this form, and we consider a 50-dimension example. This parameter c will control the smoothness of the function. We consider these two choices, and we can easily verify that when we have these two choices, we can have the computable worst case error bound for this test function. In the numerical results, we also consider the two choice of the weights. One of them is this exponentially decay weight, and the other one is just equal weight. For comparison, we'll compare the Hankel random design versus URD, uniform random design, versus the linear matrix scrambled Sobel sequence. And we also present the result concerning different choices of the base B. So the first is about the plotted squared error of the median of means estimator. Here we have two choices, C equals to 1.5. All of these three methods converges at this theoretically predicted convergence rate, which is here, because here this is a squared error. So the convergence rate order would be 5 divided by 2. And because we use the exponentially decay weight, the effective dimension is low. So in these three methods, the Sobel sequence performs the best among these three methods. But we also observe that the Hankel random design is substantially better than this uniform design because of the reduced probability bound that we have discussed earlier. And when C equals to 2.5, then we observe this theoretical rate, and then a similar behavior with this first example. And then we also tested the effect of the base, and then we consider different choices of the base, these prime numbers. But in these two examples, we didn't observe the effect of the base that has an impact on the convergence rate or even the constant in this integration error, because we observed that these convergence curves almost overlap. So regarding the greedy optimization, the first plot that we presented is the computable worst case error bound. Here we compare the Hankel design and the uniform design. First of all, we make a comparison sample-wise. That is, we can consider that we choose the batch with only a batch size 1. And alpha is the smoothness of this function class. Here we observe that the Hankel random design only has a very smaller advantage compared with this uniform design. But if we increase this batch size from 1 to 15, and then in each batch we choose the smallest worst case error bound, then here we observe this very obvious advantage of this Hankel random design over this uniform design. For both are for a 50-dimensional example. And in this greedy optimization estimator, we make a comparison using the linear matrix scrambled Sobel sequence as a benchmark. Here we plotted both the mean estimator and the median estimator in the right. So we see that in this case, the greedy optimized Hankel design is substantially better than using this linear matrix scrambled Sobel sequence. Even in this mean estimator. This is for C equals 1.5. And if we increase this C, that is, we increase the smoothness, we observe even better, more advantages from this greedy optimized Hankel random design. And we also tested in this equal weight regime, that is, all the dimensions are treated equally. Then in this case, we observe that the behavior of the Hankel random design is similar to this Sobel sequence. Okay, so from this numerical section, we observe that this Hankel random designs consistently perform better than this uniform random design. And the greedy optimization can further improve on this raw randomized designs. For example, we observed that the optimized Hankel random design clearly outperforms this Sobel sequence, and the gain becomes stronger as we increase the smoothness. Okay, so to conclude, in this work, we presented this new randomized design of the digital net, and we studied the two estimators, the median of means estimator and the greedy optimized randomized construction. Okay, so here are some references, and thank you for your attention.
Thank you very much, Yang, for this interesting talk. We have time for questions, if there are any. Alex?
Yes, a small question. Today, occasionally, I just read about random matrices, properties of random matrices. Just curious, why Hankel matrix? Could you simply take Gaussian random matrix or uniform?
Because here the interest must be in the FB, so it can only be sampled from 0 to b minus 1. I mean, these entries are integers. So you're talking about a Gaussian random variable.
Okay, I see. Okay, I have another small question, but maybe Robert asked, but then I come back.
Well, maybe just continue. Maybe you have a similar topic.
Okay, which properties of random matrix do you use? For example, distribution of spectra or
No, I'm not considering that.
So you do, but which properties are you using? Are you using any properties or not?
I don't think so.
Okay, good.
Okay. Robert?
So my question is more on a general level of how you describe the error analysis. So as I understand, you say with high probability, we have a small worst case error. Yeah.
Yes.
Did you also, did I maybe miss a situation where you had, okay, if I have a fixed, if for a fixed function, I'm looking at the probability of errors being smaller, and then I'm looking at like an error quantile for an individual function when applying this randomized algorithm. Yeah, you have an error quantile, and you can look at this for individual functions. And then you're looking at the worst case of the functions. What about this error quantile at a certain confidence level? Have you thought something in that direction, or expected error for an individual function at first, and then you're checking the supremum over all those expectations of the error?
Thank you for a very great question. So regarding this greedy optimization, because the criteria is to select the one that minimizes the worst case error from this function space. So in this approach, no, we didn't. But I think this is also related to your comment, because you see that in this worst case error, we are losing this extra 1/2 factor in this convergence rate.
Yeah, okay. So did you show the other result? Because I know there's a usual Monte
yeah,
Carlo.
So the other one
here.
is about median of means.
Okay. So yeah, because it's b to the power m is the number n, we would say. Yeah.
Yeah.
Points. So we have the rate there is epsilon minus 2 theta times alpha plus p. So with higher smoothness p, you get higher convergence, and the alpha is
alpha is this differentiability. So
differentiability, and p is like this Hölder. No, the integrability is integrability, and
but we also have this extra factor -1. So
and theta and epsilon, they come from
theta is okay. So
Okay.
I mean, they're related to some constants, and we want theta to be close to 0, and sorry, epsilon to be close to 0, and theta to be close to 1.
Okay. But you do not precisely reach the idealized rate, which would be to the -2 alpha plus b minus 1. Okay. You need to divide by 2, so the rate is actually alpha plus p and the Monte Carlo speed of 1/2.
Yes.
Okay, I see.
Okay. Do we have any more questions?
Or maybe a follow-up question if we still have time. So without the median, you would not get this estimate, right?
Without the median, we only have the Monte Carlo rate, which is very poor.
Yeah, this is really interesting. Like for an individual function, you only get the Monte Carlo rate, and only when you have only picking certain good realizations of this digital net, then if you only stick with those, which is automatically done by the median of means, then you get this rate.
Yes.
Interesting.
Okay. So if there are no more questions, then thank you again, everyone, for attending, and thank you, Yang, for this interesting talk. And see you all next week for Nabila's talk, I think it is. Yeah.
Yeah, right.
Thank you.
Thank you. Bye.
Thanks.